Are you ready? So it is a pleasure to introduce Upanshu Sharma. He is currently a postdoc at the Freie University in Berlin, and he'll be telling us about coarse-graining of differential equations. Over to you, Upanshu.
So thank you very much for the invitation, for the introduction to present my work here at TIFR. So I was just being asked the question, have I ever been to TIFR-CAM? Well, I was there like 6 years ago when I was a PhD student. And so it's great to give a talk again in front of this audience. So what I'll be talking about today is part of an ongoing story that we've been working on for the last 5 odd years. And so there are a lot of people involved in this story. Okay, before I start the talk, I should say that if anybody has any questions or anything is unclear, please let me know. So because it's much easier to, it's much harder to gauge the reaction of what's going on because it's not clear how people perceive it. So please let me know if you have any questions. Okay, so as I said, this has been going on for a while now. And so somehow the mathematics of this arose in some earlier works together with Hong Duong, Marc Pelletier, André Schlichting, and Agnes Lamaze, the top 4 people who are experts in PDEs and variational methods. But really the problem that I'll talk about today is about coarse-graining of stochastic differential equation, as the title says, but in the context of molecular dynamics. And so this really work was done with Tony Lelièvre, Frédéric Legol, who are in Paris, and Carsten Hartmann, Lara Norreider, who are more local here. And these 4, the bottom 4, are experts in somehow the mathematical aspects and the computational aspects of molecular dynamics. And so as you have noticed that I've used the word molecular dynamics quite a few times already. So that is somehow the underlying application area that we have in mind. And so in the next few slides, I want to go over a little bit about molecular dynamics, somehow to set up the stage for what we'll talk about later. Okay, so molecular dynamics is somehow a generic name given to a variety of techniques, ideas, wherein you want to extract the macroscopic properties of your system by looking at some atomistic features of your system. So more concretely, imagine you have some bunch of particles, say n of them in 3D. So I call the state of a particle X with the subscript I. And to any configuration of this particle, I associate energy value by means of a potential energy landscape U. And so this is just a cartoon to show you that typically an energy landscape, of course, is a much harder thing to visualize because number of atoms is quite large. But this is typically what it is. It's a lot of valleys together. So for instance, a bottom of a well is somehow a stable configuration of your system, and another bottom of the well is a different stable configuration of your system, right? And so in molecular dynamics, one of the interest is in sampling what's called the Boltzmann-Gibbs measure. So the Boltzmann-Gibbs measure is proportional to exponential minus the potential. That's what it is. And here Z is just a normalization constant so that the mass is 1. And what people want to do with this measure is they want to use this measure because this encodes somehow the atomistic features of your system and use it to compute somehow averages. So averages of the type, for instance, thermodynamic quantities, which means you have certain observable of your system, and then you take averages with respect to this measure mu. And then there are other quantities you could look at, for instance, dynamical quantities. And this is, for instance, how much time do you spend in a well? And of course, when I say time, I mean there is some dynamic setting. So I will come to that on the next slide. Now, these kind of questions are very typical if you want to go to computational chemistry, material sciences, drug delivery and pharma companies. So this is come out the kind of computations they look at. So really they have systems where they really understand the potential energy landscape of your system and they really want to get some feeling for the macroscopic properties. Okay, so now the question of how do you sample these probability measures? Well, the way you do it is the classical idea. You take some dynamics, stochastic dynamics, typically a stochastic differential equation, which is ergodic with respect to this invariant measure, with respect to this measure. So there are various things, various kind of equations that you can look at. Here is a small list, by no means exhaustive, but the point here is just to show you that there are various things that one can do. And I don't want you to remember any of these. So this will not play a role in what's going to happen later. But just to give you an example, so for instance, if you're interested in sampling the Boltzmann measure we saw on the previous slide, exponential minus u, then the simplest thing you can do, you can look at is so-called overdamped Langevin, which is just the evolution of the system is driven by this gradient of the potential that we saw. So it is a purely deterministic at this point, and then you add some Brownian motion to it, a square root 2 times Brownian motion. And this square root 2 will become clear a little bit. I mean, it's just for mathematical convenience. There's nothing special here. So this is called the overdamped Langevin, and this has under reasonable properties on the potential growth properties at infinity. This thing has e to the power minus u as an invariant measure, the Boltzmann measure. There are other things you can look at. Physicists love to work with underdamped Langevin. There are some non-reversible variants. You don't have to look at the details. Maybe one interesting one is this one, where you have a same system. So imagine a polymer chain. It has certain associated potential. So for instance, people want to understand when the polymer chain is crumpled together or when is it extended. And these two are two different stable configurations of your system. And then this whole chain is moving in a macroscopic flow. So there is some external forcing in the system. And people often want to understand what are the properties of this system, this XT, how does it behave? When does it bend? What are the time it spends in different configurations, things of that nature. Okay, so bottom line is in MD, you have a stochastic differential equation and you want to, which is ergodic with respect to some invariant measure. Ergodic here simply means you have a unique invariant measure. So let's forget about the word ergodic. And here I have a general SDE. So this is with the deterministic drift B and a diffusion matrix sigma and some Brownian motion WT. Okay. And so again, the question of calculating averages, which is a somehow classical question, for instance, in Monte Carlo techniques, is to say, okay, you want to calculate averages of an observable with respect to this measure. Well, instead of doing that, you can just calculate long time averages of your observable with respect to this SDE, right? So this is what you do in these techniques. And something similar can be done on for dynamical quantities where you say, okay, I have, I start off at equilibrium. I run a trajectory of this SDE. I run many such trajectories and I take averages. So this is the kind of things you do. Okay, so this would be somehow the idea in molecular dynamics. There was a keyword coarse-graining in my title, and now I'll talk about coarse-graining and why such a relevant thing in the context of MD. So coarse-graining is a name which popped up more in, I think, the simulation direct side from the simulation part of MD, where they want to reduce the complexity of the system. So you can imagine that typical systems are extremely large, very high dimensional. So just to give you an example of the scales that you're looking at, here there's a simple, typical MD simulation where you are interested in how does the ligand bind or unbind from a protein, okay? And so if you do this simulation or you look at the number of atoms only in vacuum, then you have about 3,000 atoms. So that's about 3,000 dimensions. But if you simulate this setup in solvent, just typically what happens, because these are the kind of questions you look at in drug delivery, then you have 40,000 atoms in an MD simulation. So that's an extremely large system. And the second problem in MD is that there is metastability. And so metastability means that the quantities of interest, the quantities that you really are after, evolve at timescales which are considerably larger than timescales you can achieve by just doing simple classical numerical methods. So again, to give you a feeling of this, in this particular example, what you would do is you would take one of these stochastic differential equations, you would put a time step on it. This time step would be of the order of femtoseconds, if you will, 10 to the power minus 15. But this dissociation time of the ligand is happening at the scale of microseconds to seconds. So there, as you can see, there's a huge discrepancy between what you want and what you can achieve. So this is really a problem. What else did I want to say about this, which is important? Yeah, so.
Can I ask you a few questions?
Please.
So, sorry, I got a little lost in the chemistry, so I don't exactly understand what is meant by the dissociation time and ligands binding with the protein.
Yeah.
But Perhaps it's not relevant for the mathematics, in which case you can just skip ahead. But and also, what do you mean by MD again?
Molecular
molecular
dynamics. Yes. MD is molecular dynamics, and again, dissociation time. I mean, this is just an example. There's nothing special happening here. Of course, it's for the mathematics, we will skip all this, but somehow I just wanted to tell you a real problem where people see that dissociation time means how much time does it take for the ligand to unbind from the protein. So there is a ligand attached to a protein, and how much time does it take to unbind? And so the time step, this is the event that you're after, but this event happens at the levels of seconds, and your MD simulation runs at a time step of femtoseconds. So that's somehow to show that there is a huge discrepancy between the two. I hope that answers the question.
Thanks.
Okay. So with this kind of...
Can I ask a question?
Yes, please.
So what is a basic premise for using a molecular dynamics? Is it because if I zoom out, I would think of this as like a continuum, but then when looking at this as a continuum, I might miss out on certain time scales. And if I zoom in, I will be looking at the molecular dynamics. And then at this molecular scale, there are two things which are going to happen. One is that your continuum is going to become large, very high dimensional, but not continuum, a high dimensional object. And you are also going to gain understand the time, different time scales.
Well, so the point is, in fact, that you do have handle on what's happening microscopically. So just to go back, we understand what happens microscopically. This is completely hidden in this potential U. Okay, so for instance, in this example, so you simulate your trajectories of the system using this, say this overdamped Langevin dynamics. You understand this, but the point is, you don't want to simulate the system fully. You want to look at some observables. For instance, one of the questions you would ask is, say I start off at a certain well in this potential, how much time does it, on an average, it takes me to leave the well? Or for instance, what is the typical path for me to leave the well, to go to another stable state? These are kind of the questions people want to ask.
So how does that relate to molecular dynamics? Because this question of potential well and then leaving the potential well can also be asked in general statistical physical scenarios.
It is absolutely. It can be. It is. This is.
So then how is it specifically related to MD?
It is not. I would say my motivation is from molecular dynamics, but all these questions are generally computational stat mech.
So which is why, again, I'm confused. What exactly is the motivation to work in MD?
So MD is a particular area of computational stat mech. That's what it is. Molecular dynamics is just one area of, when you really set on, this is the name given to the bunch of computational techniques which you actually use to compute stuff in statistical mechanics.
So once again, so what is the gain?
What is the gain as in? I mean,
in the sense of using this specific methodology for the numerical simulation.
Well, so how else would you, for instance, if you wanted to sample a certain measure, how else would you sample it? If you wanted to sample some quantities with respect to this measure, you would sample.
So you are saying that the Gibbs sampler is your MD?
Yep, that would be one of the things. Yes, exactly. You can also run. Yeah, exactly.
I understand. Okay, so MD is just a fancy name, or maybe it's an older name.
It's a classical name from computational fields. They call it molecular dynamics.
Okay, okay, all right, okay, then I'm fine.
I hope that clarifies the notation a little bit. So this is what you want to do, and I just wanted to say that, okay, there is a lot of complications here, and now I switch a little bit from, hopefully from MD to what the real problem is. So say, what people do is they say, okay, you have this high dimensional system, you can't really work with this in practice, I mean, even though you want to. And so what you can do is you can project onto some slower relevant variables. So just to give you a very naive example, imagine a double well potential. So I'm running a simple dynamics, which is the position of the system. Now it's just two-dimensional. I'm forgetting about dimension. I'm forgetting about atoms, just writing down an SDE. I'm running it in a potential energy, where the potential energy is just a double well potential, and I add a noise to it. And then if the wells are deep enough and you run a simple simulation, you let the particles sit in one well, it will spend an extraordinary amount of time in one well, and then it will shift to another well, right? So this is from -1 to 1. So if your interest is in capturing the information of, okay, whether is it in the left well or the right well, then it's enough to look at only the X1 direction. Don't look at the X2. The X1 direction should be enough. And somehow this is the idea behind coarse-graining. So coarse-graining says, okay, what you should do is you should project your system onto some lower dimensional set of variables, which encode or capture the slow information that you're after. And I should say at this point that building a coarse-graining map is an extremely non-trivial problem. So it really depends on the phenomena that you're looking at. And for each molecular system that you're looking at, you will have a different coarse-graining map. And the construction of a good coarse-graining map is a whole industry in itself. But so as far as we are concerned, the question then becomes, we are given an SDE, which is ergodic with respect to an invariant measure. And we are given a coarse-graining map Cosi. And then the question becomes, okay, what is the behavior of Cosi of XT? What is this lower dimensional dynamics that you will see? As you'll figure out on the next slide, this lower dimensional dynamics is not really something you can work with in practice. So what is a good approximation of this? And since we are mathematicians, we really wanted to understand what this good means.
Can I ask you a question? This is Sivaguru here.
Yes, please.
So I don't know anything about any of this. Bear with me. So why would you not choose the X2 projection? Because it doesn't have the feature of two wells?
Yeah, exactly. So if you're after the slow, if you somehow believe that the slow feature is slow evolution is across the two wells, then X2 does not encode that. And in MD, you really are interested in the slow feature somehow.
Okay, all right, thank you.
Yeah, okay. So that's coarse-graining. And so now I think I've realized that there was a lot of MD and maybe I might have confused you, but let's now go to a little bit of setting up the mathematics of this. And just to look ahead a little bit, so what I will do now is I will talk a little bit about constructing or looking at this Cosi of XT, if you will. That's what I will do. And then
Upanshu, just
yes.
I hope I remember. So what were the notations for the potential and for the
you can
the
forget
observation?
You can forget.
We don't need.
You don't
okay.
need it.
All right.
Now
okay.
you don't need anything else.
All right. Okay.
Yeah. So so now what you need is just this, that there is an XT which evolves according to mu. And now I'll make a lot of simplifying assumptions because so that it's easier to present the ideas, but all these ideas can be generalized. So the ideas are following. I start with a two-dimensional SDE. It's just, again, to make things very simple. So I use the notation with a superscript to denote the different coordinates of your SDE, if you will. And I assume that this SDE has an invariant distribution, has a stationary measure, which is a probability measure in R2. And then I work with a very simple coarse-graining map. I just project onto the first coordinate. And I should say that all these things, for instance, having a diffusion matrix, working in higher dimensions, working with nonlinear coarse-graining maps, all of this can be done. But just to keep things simple and to, I mean, this situation is enough to capture all the kind of problems that you see. Let's focus on this setting. Okay, so the first question is, what is the dynamics of Cosi of XT? Well, that's easy. That's just the first coordinate, right? Because we're projecting onto the first coordinate. So that's just the first coordinate. So you get dx1 of t is the first coordinate of your drift, p1, and the first coordinate of your noise. So noise is not two-dimensional, it became one-dimensional noise. The problem is you can't really work with this. I mean, b1 depends on both x1 and x2. So you can't really work with this. It's not closed. So somehow you have to build some approximation of Cosi of xt, which you can actually use in practice. And so this idea has been around for a long time, but it was really mathematically formalized in this paper by Legault-Lelièvre, where they said the following. So let's keep this picture again in mind. We are interested only in the slow direction x1. And so what do we expect somehow at the back of our head is that if we are interested in x1 and x1 is truly slow, then you expect that in x2, you have some sort of equilibration happening. This is what you expect. And so this was the idea they used, and they said, okay, let's write down a new variable, zt. And now, same noise, but now we average out this dependence on the x2 variable by with respect to the invariant measure. And I will explain what this expectation means in a second, but this is what you do. So essentially, you take the dynamics on x1, you take the b1, and you average out the dependence on x2 with respect to this stationary invariant measure. Okay, now I'll say what this expectation means actually. So I will be a little cavalier with my notation in the sense that I will talk of probability measures being densities and things like that, just to make things simple. So now mu is a probability measure on x1 and x2. It's two variables. By disintegration, we can decompose into two parts. The first part is the measure which lives along x1. So that is the push forward measure. And the second measure is the conditional one, which is a family of measures parameterized by the value of x1. So for each value of x1, you have a measure on the level z of Cosi on the x2 variable. And so this average is essentially taking this coefficient, b1 of, it has two coordinates in it, and averaging out the second coordinate with respect to this conditional measure. This is what you do. So I hope this is clear, this construction of this effective dynamics, because this will be a player in this story. So this is the kind of effective SDE you look at. And so now the question becomes, okay, you have this Cosi of xt or x1 of t, and you have the zt, which is approximate, but it has the property that its coefficient do not depend on time, right? So it's just an average. And so people ask the question, okay, are these things close? And they could already find out in 2010 is that, okay, this is indeed a good approximation, at least computationally. Like in MD simulation, it seemed to make sense. So then the question became, okay, are these things close mathematically? Now, there are various ways to compare the two equations. The first one is to really compare the two SDEs, right? So you just go pathwise estimates. And the problem is, and there are various works in this, but the problem is this is too much information. You're trying to compare two SDEs for each realization of the noise. This is too much information. And so the estimates are fairly limited in where they're applicable. So what we thought of was also looking at the time marginal estimates. And that is basically saying, instead of looking at Cosi of xt and zt as just the full stochastic dynamics, we compare the statistics in some way. And they are encoded in this, what I call it's called the law, the probability distribution, if you will, of x1 of t and the probability distribution of z of t. These are two probability distributions, they evolve in time. And another reason for me to talk about this instead of pathwise was the reason that I remember that TIFR-CAM is full of people who have expertise in PDEs. So this, I hope you'll get a bigger kick out of this, because these are just, the laws just solve some sort of a drift diffusion equation, if you will. Okay, so just before I get to really showing you what are the error estimates, let me quickly write down each of these objects in terms of the corresponding Fokker-Planck equations of the PDEs. And so if you don't remember any of this, it's okay. There will always be on the right-hand side something in blue to tell you what these objects are. Okay, so we start off with the reference dynamics here. This is reference SDE, the original SDE. And we call its probability distribution rho t. This is for each time t. And so this is just a notation. I put a subscript to denote the dependence on time. For each time t, the probability distribution and probability law is a probability measure on R2. And it solves a drift diffusion equation, where the drift is exactly the drift term in the SDE. And the Laplacian corresponds to square root 2 times the noise. So that's the equation that you're looking at. And again, we have a coarse-graining map. And so now the question is, what is the Fokker-Planck equation for the effective SDE, the approximate one? Well, this was the SDE with a certain coefficient p. And again, we call its law as eta t, and it is again a drift diffusion equation, now in one dimension. So you will have to forgive me for the fact that I used higher dimensional derivatives for this, but that's just so that everything is uniform and it's easy to read. So it's just a one-dimensional drift diffusion equation. That's what happens here with a certain coefficient p. And now, of course, we want to compare, as you remember, we want to compare eta t or zt to Cosi of xt. So the first coordinate of this equation. So what is the Fokker-Planck equation for that? Well, the way to see that is the Fokker-Planck equation of the Cosi of xt is just the push forward of this measure under Cosi. Okay, and so the way to find this out is just to say, okay, we take the full probability distribution. Rho depends on time, depends on x1 and x2. We project it again, like disintegration theorem, like the previous slide, we project it onto the x1 variable. You get the push forward dynamics, the dynamics of the Cosi of xt. And then you have the conditional measure, which is parameterized by x1. And so now what you have is the same equation, something similar as in the effective, but now instead of having averages with respect to mu z, you have averages with respect to rho tz. Okay, so these are the players in our game. We have an eta and a rho hat, and we want to compare them. So just to summarize, the question is, so that again, if you forget about everything from behind, just remember that you have to compare two drift diffusion equations, which are related in the fact that B hat has an average with respect to rho tz, and B has an average with respect to mu z, and this mu is the long time limit of this rho t. That's what it is. So you have to compare these two drift diffusion equations. Now, I'm guessing that the moment you see two drift diffusion equations, I mean, you're looking at your chops and you think, okay, there should be some nice way to compare these two equations in some Sobolev norm. It turns out that for these equations, we get a better handle if you look at metrics or distances on the space of probability measures. And so one such object is the so-called relative entropy. And this is what I will show the estimate in. And so relative entropy, I will show some estimate on this. And so relative entropy, of course, inspired by the notion of Boltzmann's entropy. So it has a very similar formula. It's k log w here. And so it's something similar here. For two probability measures, nu and zeta, if nu is absolutely continuous with respect to zeta, then it's with the form f log f, where f is the Radon-Nikodym derivative of these two things. Okay, so that's the relative entropy. And if they're not absolutely continuous, then it's plus infinity. So that's the relative entropy. It's not a metric on the space of probability measures because it's not commutative. It doesn't satisfy a triangle inequality, but it's non-negative. And it is zero if and only if the two measures that you're plugging into it are the same. Right? And in case it doesn't make you happy that we are getting estimates on entropy, then you can always keep this in mind that any estimates on entropy give you estimates on the total variation distance via this CKP Chisor-Kolbach-Pinsker inequality. So there is this. So any estimates that I will show you on entropy comparing these two objects will give you control on total variation distance. Okay. Now, just before not the 8th slide, but the 10th slide, I'll show you the error estimate. And just before I get there, I have to talk about, if I want to compare two things, you almost always have to have some sort of a scale separation parameter sitting there. There is no scale separation sitting here in this set of problems. So where do we get something to measure the error in? What is that object that helps us? Well, the thing to keep in mind is that there is this mu z sitting here. And this approximation was made with the idea that on the level sets of your mapping, on the x2 variable, you expect equilibration, right? And so this somehow is this inherent time scale separation is characterized by what is called a log Sobolev inequality. So a log Sobolev inequality is a function inequality, and I'll just go through it, what it says mathematically, and then I'll tell you what it means. So we say a measure, in this case, the conditional measure, again, we are going to say that this object satisfies a log Sobolev inequality. So the one inside here. And we say that this measure satisfies a log Sobolev constant inequality with certain constant if for any other probability measure which is absolutely continuous with respect to it, you can find a constant such that the entropy between nu and mu bar z, and this is a finite object because this is absolutely continuous, this is bounded by, in some sense, logarithmic gradient. So L2 norm of the logarithmic gradient. So this is a nabla log square d nu. And this is what is called as Fisher information in various fields, for instance, especially in information theory. So this is the Fisher information term. And then there is a constant in front. Now, if you've not seen this before, this might seem like, okay, what's the point of this? Why are we doing this? Well, thing to keep in mind is if you have such a log-SOP inequality, it basically means that mu z has good mixing properties. So what I mean by that is any dynamics which will sit on the level set, which has mu z as an invariant measure, will mix quickly. In fact, it will mix exponentially fast. So this is somehow to quantify the fact that you expect fast mixing on the level sets. Okay. So there are some examples. I don't want to go through them, but what I want to say quickly is.
Can I interrupt you a bit?
Yes, please.
Yeah. What do you mean by mixing properties again? And
so
could you just explain mixing?
So for me, I mean, the way I would say, okay, I'm being a little bit quick with what I mean by mixing. What I mean here is specifically that if a measure satisfies a log-SOP inequality, it means that any dynamics, any reversible dynamics, which has this measure as an invariant measure, will converge exponentially fast in relative entropy. Will converge exponentially fast to the equilibrium in relative entropy. That's what it means. So somehow for me, okay, mixing maybe is not the right word or not the mathematically correct word, but the right would be somehow that you have fast equilibration on the level sets. That's what I would mean. Yeah. And so if you want a picture in mind, and we had this potential at the very beginning, U, and we said, okay, there is a fast direction and a slow direction. So just to give you an example, so it's very hard to find this log-SOP constant. So it's easy to say, okay, which kind of measure satisfies a log-SOP inequality, but to find the constant is hard. But just to give you an example, think of the double well potential we had again. So in one direction, so this is an additive potential. In one direction, you have this is the slow process because it has a bump it has to go over. And in the x2 direction, you have a quadratic potential, right? And in this simple example, this conditional measure will have log-SOP constant, which is exactly the lower bound on the Hessian of the quadratic potential. So it's a very simple, specific example to keep in mind if you want. And some of this should also say that what you're expecting is that along this direction, the dynamics will not converge, might not converge as fast as it will converge in this direction. Somehow the orthogonal direction equilibrates faster. Okay. So with this kind of assumption in mind, we can now present the main result. So again, just to remind you of what are the different players in this game, we have a reference dynamics, a drift diffusion equation living in, so rho is a probability measure on R2. It has an invariant measure mu. So what does that mean? That if you plug in mu here in the right-hand side, you get 0. So it is really an invariant distribution for this dynamics. You have this reduced dynamics, the Fokker-Planck equation for Cosi of xt, or the first coordinate, x1 of t, right? And then you have this approximate dynamics a la Lego-Lelièvre, which said, okay, you can average out with respect to the invariant distribution. And the question is, how close are they? Well, first of all, we need to assume, of course, I call it ergodicity on level sets. I have all kinds of names, mixing, but essentially what I mean is equilibration on the level sets is mu z satisfies the log-SOP inequality with a certain constant. And the second thing you need to have is somehow the fact that you see in both these equations, you have averages with respect to B1, right? And somehow you need that this B1 does not interact too strongly with the x2 direction, right? You don't need to be too strongly coupled, or at least we need it. For estimates to work, we needed to have some reasonable coupling in the two directions. And that is somehow encoded in this definition of this kappa. So it's somehow, in some sense, it's a Lipschitz constant in the x2 direction of B1. Okay, and with these two assumptions, you can show that you have an estimate of the following type: the relative entropy of rho hat and eta are bounded by the initial data plus constants kappa over alpha LSI square, and then you have this relative entropy objects, which is somehow special. It is the relative entropy of the full dynamics, the full system that you have with respect to the invariant distribution minus the relative entropy at time t with respect to the invariant measure. So this is somehow the main estimate in the story, if you will. Any questions? Okay. If not, then I talk about a few remarks
Actually,
about.
I have
Yeah.
a question.
Yes. Yes.
So if you go back to page 9, the simple example that you
Yes.
showed us, the Hessian basically of the quadratic thing in the slices, the lower bound on that is your constant, right?
Yes.
So more generally, you would expect some kind of, I don't know, geometric information, eigenvalue of some kind of Laplacian or perturbed Laplacian to show up
Yes.
there, right?
Yes.
So what is the what information of that sort can you find in the result that you flashed in slide 10?
So we don't make any. So the point is we don't make any. We don't talk about any specific potential. So it's really tough to see what exactly the constant is. We just assume that there exists some constant like this.
I see.
Right. But the point is, if you were to think about this, so at least in certain simple examples, for instance, here, you can actually link it to a spectral gap, as you said. It connects very naturally to the spectral gap. So one way to think about this log Sobolev inequality is maybe a naive way, if you will, is that it is somehow a non-linear version of the Poincare inequality. You just linearize the logs around the object. So you get somehow like the derivative of this thing square. And similarly for rho log rho, you linearize the log again. So it's like a non-linear version of the log Sobolev inequality. And in fact, this inequality implies the Poincare inequality. Well, of course, on a weighted space with the right weighted measure. So there are some connections there, but at this level, we only make an assumption that there is a constant that exists such that we can say this.
Okay, thanks.
Okay. Okay, so we have this estimate. So just one remark, because if you look at this, you would say, oh, yeah, I should say this. If you look at these two dynamics and forget about all the estimates, just look at this object. You would say, as t goes to infinity, we know that rho converges to mu. That means this will converge to that in long time scale. So in some sense, there is a discrepancy in this estimate that it does not capture this long time decay. And that is a problem. That can be fixed, but I don't want to go into details of that, but there is somehow some discrepancy in the long time behavior. And another question you might have is, okay, the right-hand side depends on time still. So what's going on there? Well, it turns out one of the reasons to pick up relative entropy is that it's a Lyapunov function for Fokker-Planck equations. So what do I mean by that? That the relative entropy with respect of any two solutions. So take a Fokker-Planck equation. It has a solution rho. Mu is also a solution, although it's an invariant solution, an invariant distribution. And you take the relative entropy, you differentiate it in time, and you will find that it decays. It's a negative object. So that means entropy always decays, which means you can control this whole term by just the initial term. And so essentially what it gives you is that you have a uniform in time estimate. But as I said, it's not the best thing you could have. You can improve it, and well, that's a different issue. Another point of view is that you can have other estimates as well. You can do it not in relative entropy, but Wasserstein distance. But then it turns out that we get really bad scaling in time. If we get an exponential scaling in time, it has some other advantages, but scaling in time is bad. And finally, I want to make a remark in this and connect it to the averaging literature. So you might have a question, okay, you proved this estimate, it looks nice, but is it sharp? And so if you want to talk about the notion of sharp, we need to introduce some sort of a scale separation to the system. So if you introduce some sort of a scale separation, so specifically this coming scale separation from averaging. So here I have, again, the same setup. I'm writing down the SDEs, the first coordinate with B1 and the noise, the second coordinate with B2 and the noise. And now I introduce some small parameter epsilon in there, right? And so you can imagine that what this means is that X2 is moving as a time scale, which is considered is 1 over epsilon. So you can expect somehow that it averages out. And that means in our context, you can project onto the slow variable, which is the X1 variable. So then you can repeat this whole story I showed you with effective dynamics and projected dynamics, write down the estimate, and you get exactly an epsilon popping up in the estimate. And this epsilon is indeed sharp, at least if you look at numerical examples. So this somehow, even though our estimates that I showed you, the results that I showed you are in the absence of scale separation, if you did have scale separation, these results are quite sharp. Okay. Now I have, I think, another 10 minutes to go. So I just want to spend some time talking about how does one go about showing such a thing.
Upanshu, I have a question.
Yes.
So if I look at the completely decoupled system in which the coordinates are completely independently evolving in time.
Yes.
So that is to say that your B function, little b, b of x1 comma x2 is just b1 of x1 comma b2 of x2.
Yeah.
So in such a scenario, I'm just trying to wrap my head around the result that you had shown on the previous slide. So you are basically saying that when the mu z satisfies the log-Sobolev inequality, then you have this result.
Yes.
So I got stuck at the previous step. You are not making any statement about what kind of b will give you a mu which will have which will satisfy the log-Sobolev inequality, right?
Yeah, that's a good point. Yes. So what? Yeah.
So that is my question. So I mean, so your result is based on this assumption that the invariant measure has this very nice structure on this.
Has a log-Sobolev inequality. Yes.
Right. That's correct. So, but I mean, that itself is quite hard to check, isn't it?
No, it's reasonable. So for instance, anything, if you take if your B is linear at infinity, typically. Okay, so let me start off with this. All these things are happening in unbounded state spaces. I'm working with R2 and R1. So in practice, if you want to, first of all, if you want to work with bounded state spaces, so torus, work with periodic boundary conditions, if you will, then it holds automatically. Because on finite state spaces, everything is fine. You don't have to worry about anything. Now, if you want to work with unbounded state spaces, as I'm doing in this case, then of course, you need to be careful. So one of the examples would be, so for instance, if you would have B, which is of this form, this is just an example. It's of this form, then you need that, okay, more generally, you would need that log mu z scales super quadratically. So you need some sort of growth conditions on mu z. So if you have a Boltzmann measure in mind, exponential minus v, this somehow means that the mu z, the scaling in the orthogonal direction, not the projected one, but the level set, really has some sort of sufficient growth at infinity to have, you just need sufficient growth at infinity. That's all you need. Not
so
sure
specifically, basically like log concave measures would satisfy this, right?
I think so, yes. So log concave are the things which on a bounded domain go through bumps.
V will be convex.
Yeah, exactly. Yes. Exactly. Something like that, yes.
Okay.
Yeah, but you're absolutely right. This is here we have completely removed the fact that we are not saying when it will satisfy log-Sobolev. We can give you examples when it will, and it's a reasonable assumption. But if you have log-Sobolev, then you have this estimate. You're absolutely right.
I see. So there is no result which basically tells us, like, for example, what I was thinking. Sorry, I mean, it's going a little all the orthogonal direction in the sense like so completely decoupled system. It's like you don't have that issue of the reduced system or
exactly. It's just
you don't have that problem at all. But if your second coordinate is influencing the first coordinate in a very like the effect is very little. Is there a very way of quantifying that and like getting around this problem, or you did not think along these lines?
So I don't know what exactly do you mean by, so imagine here is an SDE.
Basically something like what I think people in PD talk about observability and controllability, and like that.
Okay, so I have not much
so
idea
if
about
you
these.
have if you have some information, some observable on the process X, is that good enough information to derive all the information about XT? So that is basically some sort of observability in some sense, in a very vague way. So, and what you are doing is also something similar, because basically what you have is XT is a diffusion, whereas the the new variable X1, the projected one, is not a diffusion, and which is why you're running into trouble. So which is why you want to have this approximations and all these things.
Yeah, sorry. So I don't completely understand the link here, but I'm happy to talk about this if that's okay.
That's okay.
Because I will really spend.
I mean, it was a question.
No. I will need to figure out what exactly do you mean by this connection between the different directions. I think if we can sit down and write it out, then I think I can tell you what exactly do we know and not. Okay. Thank you. Okay. So I just want to spend some time, last few minutes, to talk about how does one prove this estimate, and somehow. as far as I'm concerned, this is really the cool part of the story. So this is the story, this is the part which connects from, we're talking about PDEs here, it connects to the theory of large deviations. And I will not do it in great detail, but I still want to reflect on this connection a little bit. So for the moment, if you just forget about all the things we spoke about before. We know we want to compute the entropy distance or relative entropy of two objects to drift diffusion equations. But for the moment, let's forget about it. Let's just look at an SDE, a simple SDE, and it has a corresponding Fock-Planck equation, which is a drift diffusion equation. And here L is just, I'm writing it out like a generator applied to eta. Okay. And so one of the questions is, how does ZT connect to eta? Well, there are various ways to see this, but one of the ways is to say the following. You consider some independent copies of ZT. So Zi is the state of the ith particle, and this does not interact with other particles. So the Brownian motions are independent. And then you look at what is called the empirical measure. So that is like looking at the averaged state of the system, right? Look at n particles which are evolving, each of which is evolving according to this SDE independently, and then look at the empirical mean or empirical measure. And then it turns out that as the number of particles goes to infinity, this random object converges to a deterministic PDE, and this deterministic PDE is exactly this Fock-Planck equation, right? That's a very classical connection. In fact, in this case, it's quite simple. You don't even need Ohlschlager. They are very classical results in probability theory. Okay, large deviation tells you more. Large deviation tells you that this convergence happens exponentially fast. It somehow quantifies the rate at which this convergence happens. So again, putting a lot of details under the rug, it essentially would say, what is the probability? It talks about what are the probabilities that eta n behaves like some nu. This nu need not be eta, some nu in the limit of n going to infinity. And it says that in the limit of n going to infinity, this probability scales exponentially. And the crucial object is this I, which is called the large deviation rate functional. This large deviation rate functional is non-negative, and it is zero if and only if the object that you put into it solves the PDE that you were after. Okay, so what does that mean for us? It means the probability of not seeing eta decays exponentially fast, right? So in some sense, this I, the non-zero values of I, capture the error that you make when you step away from your correct limit, right? And that's the thing to keep in mind. And it has a specific, in this particular example, it has a nice form. I won't tell you what this star square term means, but essentially, if you look at this, it's like a norm square, informally, a norm square of time derivative minus L applied to nu. Nu is arbitrary. So you can imagine if nu solves the equation, this is zero, and otherwise it's non-negative. Okay. And so why I'm talking about this, it turns out that this I, this rate functional, links very naturally to relative entropy. So again, so I talked about this briefly initially. So a few slides ago, sorry, where I said, okay, these are these Fock-Planck equations. They have this property that if you take any two solution of this Fock-Planck equation, so take eta and nu, both solve the same equation, relative entropy is a Lyapunov function. What does that mean? The time derivative of relative entropy is the minus the Fisher information. We saw this in the log-Sobolev inequality. It is some object which is non-negative. Okay. This is what, if you look at the time integrated version, this is called the energy dissipation identity or energy dissipation principle. It has various names. But what we want to do is we don't want to compare solutions to the same equation. We want to compare solutions to two different equations. Now, it turns out magically that if you plug in an arbitrary nu here, you get an error, and that error is exactly the large deviation rate function. And this is, for me, quite fascinating, because if you look at this, on the left-hand side, you have objects which have completely to do with the macroscopic properties of your system. So you have a PDE. This tells you how some Lyapunov function evolves, what is the dissipation rate. But on the right-hand side, you have this object which encodes really the stochastic features of the underlying particle system, right? So this is somehow a very interesting connection. And just to point out, this is not a fluke. This somehow is a very general connection which connects to Wasserstein gradient flows, non-equilibrium statistical mechanics. It appears even if you deal with non-linear, not only linear in eta, but non-linear equations. So this is quite a general phenomenon. But okay, how do we use this? How do we use this to, how do we leverage this inequality in our setting, is that we look at this reduced dynamics and this effective dynamics, we plug them in, we get this Fisher information, and we get this rate function. Now this Fisher information doesn't matter what the form is, it's non-negative, so you can get rid of it. And all you have to do is now estimate the rate function. And in this particular example, where you exactly know what the two things you are putting into the entropy are, it turns out to be just the difference of B minus B hat square. It's just a weighted L2 norm, if you will, of the difference of drifts. And now I won't go into the details, but essentially using this log Sobolev-Talleyrand inequality, using some coupling arguments, you can get the estimate in the end. So I don't want to go into the details. The only thing I want you to remember is that somehow you can use this connection to large deviations to really get some macroscopic control on your error. And that's somehow the useful bit. And in the last, say, 2 minutes that I have, I want to quickly summarize what we spoke about today. So probably it was not the best idea to talk about MD so much, but we were interested in coming from questions in MD where they really want to simulate some SDE. And the problem is you can't really simulate it because it's very high dimensional, there is metastability. So what you do is you usually project the system onto some lower dimensional set of variables via this mapping Cosi. And then the question becomes, okay, what is the dynamics of Cosi of xt? You can't really work with this, so you work with some sort of a closed approximation of Cosi of xt, which we call the effective dynamics. And then assuming we have certain equilibration on level sets, we showed that the effective dynamics is indeed a good approximation. That's what I showed. The mathematical techniques involved are somehow entropy techniques and function inequalities. There was this very interesting connection. Hopefully I gave you some flavor of what the connection is to large deviations. And again, we have no explicit scale separation. So because any mathematical result, if you see on this kind of a setting, is for when you have an epsilon sitting somewhere. And if you go to a practitioner, he says, hey, my system has no epsilon. So I don't know if there is scale separation, but I guess this should happen. So like there is a feeling that there is some sort of scale separation, but it's not so strong as we see with epsilon. Okay, if you're interested in this, this kind of question, then how this links to molecular dynamics, I would suggest you to read this first paper by Lego-Lelievre, which was somehow a seminal work in this direction, which made it mathematical. All the results I showed today are in this paper with Lara Norreider and Carsten Hartmann. And if you're interested in this connection of large deviations and Wasserstein gradient flows, we recently put up a paper on arXiv, and its introduction, we tried to explain these connections a little bit. One last slide, and then I end it in the last 2 minutes. And this is about, is it okay if I take 2 more minutes or?
It's fine.
Yeah, okay. So this last slide is about, okay, I showed you all these things. I started off by saying MD, statistical mechanics, practitioners. If you go to practitioners with this equation, the first thing they would say is, you have a coefficient, you take averages with respect to a measure on the level set of a mapping of a nonlinear function. How do you do this efficiently? Because I don't want to spend so much effort and energy into implementing this and then find out that it does not give me any gains, right? That's the question that a practitioner will ask. And mathematically, the challenge of sampling measures on level sets is that if you build any numerical method on level sets, what will happen is typically you will build an SDE, a stochastic method, a stochastic dynamics. Because you use stochastic dynamics, you will leave the manifold. Any kind of dynamics will move you away from the manifold. And then the mathematical challenge is how to project it down to the manifold. So this somehow turns out to be really a question for people who want to compute these things. How do you project things back? And this is quite a non-trivial question which appears elsewhere as well. The second question, I think, which hopefully tickles you a bit, is physicists don't want to work with often don't want to work with equations which have non-degenerate diffusion. So they want to work with what is called the underdamped Langevin equation, where you have xt, which is the position of your system, but also pt, which is the momentum of your equation. So all your system, each particle has a position and a momentum. And then they add noise only to the momentum variable, right? Now, this is really tricky mathematically. It makes a mess because if you write down the corresponding Fokker-Planck equation, rho t, which now depends on xp, it has diffusion only in one variable. So it leads to this degenerate diffusion situation. And so a lot of the questions of coarse graining become extremely hard to answer. And so this is somehow, both of these directions, something we're working on, but it has got lots of open questions and a lot of interesting ideas. And with that, I'd like to thank you for your attention.
Let us thank the speaker for a wonderful talk. Any questions for the speaker?
So to summarize, you are basically giving us or telling us that whenever you do those conditions are satisfied, you can actually sample you can actually compute those observables, right?
Yes.
Like the moments of those observables, and
Well,
compute those moments.
Well, so what you can compute is, you can't really, if you look at the original dynamics, you can't. So you project the system down and then you can calculate with respect to the projection. Yes.
That's right.
Yes,
So
exactly.
that is like one of the takeaways. Would you say
Yes.
that?
Yes. So somehow there are reasonable lower dimensional approximations which you can use in practice. This is one of them.
Use in the sense of what?
Well, so use in the sense that where is my? So use in the sense that you have some, okay, maybe that's not the best place to look at it. Here. So you have a full dynamics, right?
Mm-hmm.
You can't work with this because it's too high dimensional. Well, you would like to work with this, but you can't. So what you do is you project it down. You can build a nice closed approximate dynamics. But if under reasonable conditions, this is the right thing to work with. That's what I'm saying. So instead of looking at the full dynamics, you can just average things with respect to this dynamics, slower dimensional dynamics. Yes.
Okay.
Yes. I'm not sure if that answers completely the question, but hopefully.
It does.
Yes. Okay.
Any further questions?
So once again, so the results that you showed, that were specifically for the chosen projected psi, or were they general? Sorry, I forgot.
So all these results actually, I mean, I didn't talk about this, but you can work with any SDE as long as you have reasonable growth conditions and things are not too nasty. But Cosi can be nonlinear function. Again, as long as things are well posed, you don't have to worry about the actual well posedness of the equations involved. And then in that case, you can actually prove results. And so typically the results are divided into two parts. So what you would call reversible diffusions, or when the generator for this process is self-adjoint in some space, then you would have a lot of results because things become quite explicit in that case.
Mm-hmm.
And then the results we have are
because the dynamics is also reversible.
Exactly. The dynamics is reversible. You have a nice invariant measure, which is the Gibbs one, and all the things are nice. Everything is explicit and everything is nice. The things that I showed you today is really about general SDEs. And so you can work with general SDEs and general nonlinear functions, nonlinear mappings. So all these estimates work in that case.
Okay. Can you go to the last slide? I hope I'm not stopping others from asking questions. So here, when you're saying about, when you're talking about the projections, I'm not entirely sure, but there are some of these von Mises type of distributions which actually they don't run out of this manifold; they stay on the manifold all the time. So I mean, but okay, not all manifolds. I am only talking about sphere, for example, which is a very nice parameterization. Perhaps due to the nice parameterization, it stays always on the sphere. So I mean, have you guys already started working on these kind of things? Yeah, we have some results. We have already some results on this. But the point is, if you're thinking about these kind of constructions, the computational challenge is you don't really want to use the higher derivatives of Cosi. You don't want to do that in practice. So that really limits how you can use it. So you really can't use this constrained Brownian motions typically, because if you want to work with them, you really need to have a strong understanding of the geometry of your
of your manifold. So you typically, what you do is you build some samplers, which is just like samplers in usual Euclidean space, some sort of and then project it back. Exactly. That's that's the way you go about it. Yeah.
Okay. And for the second question, the underdamped longement.
Yeah.
So here, I mean, there are several people who actually do this, but using some sort of an approximation. What they do is they introduce an epsilon noise in XT, and then study as epsilon goes to 0. Of course, I mean, this will all now depend upon how V behaves and several other things. So, I mean, why are you, so what is your approach going to be, and why are you not following their approach?
So the way to think about this is, if you're doing a PDE techniques, so if you look at time derivative of relative entropy, because that's what you're really after, time derivative of relative entropy will give you only a gradient derivative of Fisher information, which only depends on P variable. It will not give you the Q. And so you're saying, okay, add an epsilon regularization and you're in business. Well, it turns out that's not enough, especially for the things we want to do. So you have to now do something slightly different. This was really formalized. I mean, it's an old idea, but formalized by Villani in this memoirs hypocursivity, which said, okay, you don't want to look at just relative entropy. You want to look at relative entropy plus epsilon times entropy, which accounts for the, so these operators, they're hypoelliptic. So even though there is noise only in one direction, it is enough to somehow move the noise into the whole system. So these are the kind of techniques you want to use, hypocursivity, but just adding an epsilon times a regularization doesn't really work in this case. At least not, and also because we're interested in long time behavior, like we want to talk about convergence to some sort of invariant measures, this doesn't really work. It really poses a problem. But you're right, there are techniques out there. The one you're mentioning, I don't think works as it is, but there are other works out there.
Are there other questions from the audience? Okay, so let's thank the speaker again for the wonderful talk.